Friends, let us continue our discussion on design of reactors for ammonia synthesis, and we will try to look at some of the design aspects considering even the non-isothermal reactor design. So, where we stopped in the last session was looking at these balances for ammonia synthesis, namely the mass and energy balances, and realizing that this is a fixed bed reactor. So, we have the energy and mass balance which look something like this. We also discussed that we need to introduce the idea of effectiveness factor, because this is a catalytic reaction. So, there may be some mass transport limitations associated with the performance of the catalyst. Now, what we are going to do is, for sake of discussion, we will neglect these diffusional limitations at the present moment, because I want to illustrate the idea of how non-isothermal reactors are operated and so on. So, let us for time being just focus on assuming this effectiveness factor value is unity. It does not change qualitatively any design aspect. So, before we now go to the actual reactor design and look at various operations, let us go back to the case where we had earlier considered that what happens when you have a reaction which is reversible and which is exothermic in nature. So, our ammonia synthesis reaction, for example, the reaction which we have is characterized by two features. One, it is a reversible reaction. Number two, it is a exothermic reaction. So, we know that equilibrium extent of reaction decreases as we increase the temperature, but this is not the only thing. Temperature is not the only thing that is changing in the reactor. Our extent of reaction or reactant concentrations in turn are also changing. So, to look at the behavior of such reacting system, let us go back, and we have already discussed this, but I will repeat it. Let us say that we have a exothermic reaction A1 going to A2. So, rate of this reaction, for example, let us write this as forward rate constant and this as backward rate constant. So, rate of this reaction is Kf into C1 minus Kb into C2. We now express C1 and C2 in terms of extent of reaction, which are obviously related to each other. So, C10 into 1 minus alpha minus, let us assume that there is no A2 present in the beginning. So, this will be simply C1 into alpha, or in other words, we will have reaction rate, which is, if I take Kf and C10 out, will be 1 minus alpha minus alpha by K equilibrium, because K equilibrium is nothing but the ratio of Kf by Kb. We have seen all this. So, we know that this is a function of temperature, this is a function of temperature. So, let us try to look at what will happen to our rate of reaction, or in general I can write my rate of reaction as a function of progress of reaction alpha and temperature in the reactor T. Now, let me rewrite this, and we had discussed this earlier, that at the beginning, that is when alpha is 0 and we have certain temperature T, what will happen to the rate of the reaction? Alpha is 0. So, the rate will be governed by the first term over here. Now, here there are two different factors which determine the rate. For example, if we say that we will look at this expression in the following manner. Let us say that we look at this variation of rate in the domain of alpha and temperature. So, let us say that we want to look at how this rate will change in the phase plane of temperature and alpha. So, in this phase plane, a two dimensional plane, we are going to plot the contours such that the rate of reaction is constant. So, first constant, so we are going to plot contours of R equal to constant C, and the first constant that we can plot is when C is 0, that means we have achieved our equilibrium, and that contour I will represent it by this blue line over here. So, for this blue line rate is 0, that is my contour. Now, let me try to draw contour for different values of this constant C1. But before we do that, let us try to qualitatively understand how this rate will vary. Since rate is a function of both alpha and t, we will for sake of argument say that we are looking at what will happen to the rate as I change my temperature while maintaining alpha constant. So, let us say that I pick some value of alpha, alpha and fix it and vary this temperature and see what will happen to the rate of this reaction. So, in this expression over here I have fixed alpha value and I am just going to change temperature. Now, we know that at low temperatures reaction rate at the start of the reaction, let us say we have chosen a alpha value which is small. So, let us say we are somewhere in the beginning phase of the reaction, and if temperature is low and the reaction is just started, the rate constant Kf will have a small value. The contribution due to second term over here will be small because we are just at the beginning. So, there is not much E2 in the system. So, let us say that we have some point over here for which my rate has a value C1, a low value. Now, I go on increasing the temperature. So, you expect that the rate of reaction will increase. Indeed, if we travel along this line, horizontal line, compared to this point, the rate at this particular temperature will be slightly higher. The rate at some other temperature will be even higher. So, dot represents lower reaction rate, star or cross little higher, square little higher. Now, will this rate keep on increasing indefinitely? I know that at this intersection point my rate is 0. So, if I have started with a low value of rate and if I am increasing this rate, at some point of time the rate must start decreasing so that it goes to a 0 value. Once again, I am looking at what will be my value of rate if I fix a value of alpha. So, this horizontal line and keep changing the temperature. So, at low temperatures I will have some rate which is of a low value. as I increase temperature, the rate will increase, primarily because the rate constant Kf is increasing. The contribution due to reverse reaction is still very small, and therefore, the net result is increasing the value of the rate, and so if I keep further increasing. But I also know that at this intersection point the rate is 0. So, this rate from a lower value will start increasing, and then at some point it will reach a maximum value, and then I will have another point over here which has the same rate, it will start decreasing. So, this rate value will be same as the rate value at this particular temperature. So, at these two temperatures rate values are same. Then once again I will have this point where this at this temperature the rate is same as the rate at this temperature. So, we have increasing rate and then decreasing rate, and it will go to 0 at this particular point. Now, I can repeat the same exercise for a different value of alpha, and once again I will find that I will have some temperature at which rate is same as this, and once again the same argument, or in other words I will have, if I now join these points, for example, what are the contours of constant rate? I am just joining the point on which the rate value is constant. So, let me say that I will now join all the points where rate value is C1, and that value, that contour will now pass through all these dots and look something like this. So, that R is equal to C1 over here. If I do it for a different value, let us say I do it for this particular value where R is equal to C2. So, if I join all those points, my contours will look something like this. What is my characteristic? My equilibrium line is R is equal to 0, another contour R equal to C1, another contour R equal to C2. So, R equal to C1, C2, my different contours, and C1 is less than C2, and so on. So, this is how my contours will look like. Okay. So, what is the characteristic? So, let us actually look at how these contours in reality look like. So, if I plot those by taking the appropriate value, what we are looking here is the temperature on this axis and extent alpha. So, whatever we qualitatively discussed, we are looking at it pictorially by saying that these different colors represent different values of rate. So, this is a value of rate from a low value which is dark blue to a brown or red which is a high value of rate, and this particular violet line is R is equal to 0. So, what is happening? By taking the same logic as before, if I say at this value of alpha which is 0.1, if I just draw this line, what will happen? As I mentioned earlier, rate will start with a low value, go on increasing. You know the rate is increasing because the color index is changing in this particular manner. So, rate is increasing, reaching a maximum value, and then again it will start decreasing before it goes to a 0 value. So, in other words, our contours are of this particular nature, as we explained below before. So, now what will happen to my reactor? So, let me erase all these things. So, let us go back and look at this reaction rate further. So, what we are saying is the rate value is increasing, reaching a maximum value, then decreasing further, right. So, let us try to look at what is the characteristic of this particular point. At this point, what is happening? Alpha is constant, and with temperature the rate value is increasing, reaching a maximum value and then decreasing. So, if we were to express this characteristic of this point in a mathematical term, what is happening with respect to temperature? The rate has a maximum value, and rate as a function having a maximum value at temperature T has a characteristic that del R del T, the gradient must be 0. Why not total derivative? Why partial derivative? Because we are keeping alpha constant. So, at a constant value of alpha, derivative of this rate expression over here with respect to temperature reaches 0 value, and this is what will characterize the rate being maximum. Now, I can identify all such points. For example, at a different value of alpha, let us say this is that point, at another different value, this is those points. I can identify all those points, and then if I join, I will get another trajectory whose characteristic is del R del T at a constant value of alpha is 0, and this is how that trajectory will look like. The white line that you see in this has a characteristic that on this particular line del R del T equal to 0. Okay. So, this is how that reactor design, how that rate will change. Qualitatively we discussed it for a reaction A1 going to A2, but you can take my word that for reaction N2 plus 3H2 giving 2NH3, same reversible exothermic reaction, the behavior will be exactly identical. Okay. So, now let us say that we have our packed bed reactor, we are passing ammonia, nitrogen and hydrogen from one end and taking out ammonia from other end along with unreacted nitrogen and hydrogen. Now, let us try to look at in the same phase plane how would we carry out a reaction, or when we carry out a reaction what would happen. Now, we talked about two different kinds of reactor operations, isothermal reactor and adiabatic reactor. But let's try to look at, to begin with, what happens when you have an isothermal reactor. So, let us say that I have an isothermal reactor and I am going to maintain the temperature constant. Now, to visualize what will happen in the reactor, we can what is changing in the reactor as the reaction takes place. There are two things that can change: extent of reaction alpha and temperature. So, what we are saying, for isothermal reactor, temperature is fixed. So, if temperature is fixed, let us say I fix that temperature value over here at this particular value. So, if temperature value is fixed, that means I am looking at a vertical operation which will progress along this vertical line, because my temperature is fixed. And typically what happens to the extent of reaction? At the beginning it is 0 and extent of reaction will progressively increase. Extent only increases, we saw that extent of reaction is a positive quantity and it can increase and eventually reach a saturation value, which could be maximum extent of the reaction. What is that maximum extent for this particular reaction carried out at this temperature? It is this point, because sorry, not that point. It is this particular point when r is equal to 0, because we can't have our extent higher than that. So, now let us say that we now try to visualize what will happen to the extent of reaction along the length of this reactor. So, if I travel along with this length or distance from the inlet, what will happen to the extent, and I will plot that over here. So, length versus extent of reaction alpha, temperature is constant. What is my limiting value? Let us say that my limiting value is alpha at some temperature T max, and that value is this value over here, So, what will happen to my extent of reaction? Starting with a 0 value, notice what is happening, extent is always increasing, but at what rate is it increasing? Notice the color change. I hope you can see it, but if I take the temperature point over here, then you will be able to see it more clearly. Suppose if I am going isothermal reactor at this particular temperature, you see by color you can make out the reaction rate is decreasing. So, the reaction rate is maximum at alpha equal to 0 and then it is progressively decreasing. Okay. So, what will happen? My alpha will change and go to a saturation value. Why is that? Because I have maintained the temperature, for which my equilibrium constant is this particular value, let us say, and so I cannot whatever length of reactor I take, I cannot increase my equilibrium conversion higher than my conversion higher or my extent of reaction higher than the equilibrium extent of reaction. So, this is the limit and the rate is maximum at the beginning and will go on increasing in this particular manner. Suppose this was at temperature T2, okay, T2, then what will happen at temperature T1? Let me see if we can see. Suppose this is my temperature T1. I think I need to use a different color because we are not able to see much. So, let us say this is my temperature T1, this particular point. Okay. So, what will happen at temperature T1? At temperature T1 my equilibrium conversion is higher, but the rate is low compared to this temperature. So, I will take enormously long time to reach that saturation, if at all I reach it, or in other words, let me plot it. This will be at temperature T1, and at some other temperature T2, a lower value, but lower equilibrium conversion. So, this is my length of reactor, this is my extent of reaction alpha. What is T1 and T2? T1 is less than T2, that is what you expect in a exothermic reaction, reversible exothermic reaction. So, the point is, if you carry out this reaction in an isothermal reactor, you will reach saturation, and no matter what you do with your reactor, if you increase the length of reactor, you will not get higher and higher conversion. So, that is how we have determined our isothermal reactor behavior. Let us try to look at what will happen if my reactor is operated in an adiabatic manner. And for an adiabatic reactor, let us see how this reactor performance will look like. Okay. So, my adiabatic reactor. Okay. Let me erase this also. Okay, let me keep that. So, let us say that we are going to operate an adiabatic reactor and try to look at length versus extent of reaction alpha. Okay. Now, what is a characteristic of adiabatic reaction? We had seen earlier that for an adiabatic reactor, assuming that if all the thermal properties, heat of reaction is independent of temperature, alpha and temperature has a linear relationship. So, let us say that we have, let's try to take let us say that we are trying to look at how this reactor performance will be if we carry out an adiabatic reaction. So, I am going to carry out an adiabatic reaction, let us say by starting at this temperature 500. And what is my adiabatic line? My adiabatic line is a straight line. Along a straight line with certain slope. Isothermal line is a vertical line, but this is line with certain slope. So, this is my isothermal operation, this is my adiabatic operation. So, now what will happen to the extent of reaction as we change the length of a reactor. So, again we start from this particular point, and then we see that as we are increasing as the reaction is progressing, what is happening to the temperature? Temperature is increasing, because this adiabatic reactor, no heat removal, exothermic reaction, So, it adds to the energy of the system, and the energy released by the reaction adds to the energy content of the system, and the temperature keeps on increasing. So, what will happen as temperature increases? Let us travel along this adiabatic line. Reaction rate having certain value, the rate is increasing. Look at the color slide, rate is increasing as we are traveling in this direction. However, there comes a point where we see that the rate is once again decreasing. You see the change in color, eventually reaching a 0 value. So, what happens? What happens to my adiabatic reactor now? Extent is increasing as before. So, if I plot the extent of reaction versus length of reactor starting with a 0 value, initially I will have a rate which is some value, but then it will increase. Unlike this, the rate here will increase initially as my temperature is increasing, as I am traveling along the length of the reactor. It will increase, reach a maximum value over here, and then start decreasing. So, and once again I will reach a saturation value. Now, the same as initial temperature isothermal, I would have got a higher conversion, okay, but in a longer time, because the rates are lower. You can see the color scheme. The rate along this vertical line are in general lower. So, even though we are getting higher equilibrium conversion, those are obtained with a lower rate, whereas along the adiabatic line the rates are progressively increasing, at least compared to what would happen with the isothermal line. So, rates are increasing, but then again you go and hit the saturation, and that to a lower value of value. So, you hit a saturation, but much faster at a lower value, but much quicker compared to an isothermal operation. So, clearly both isothermal operation alone or adiabatic operation alone are not sufficient, because they will not give you the maximum conversion or desired conversion that you want. So, how do we run these reactors then? What we are seeing here now, this is a different white line than before. So, what is happening along this is, along the adiabatic line, the point where the rate is maximum are all joined. So, you can start at different temperatures and travel along these adiabatic lines and see where the rate is reaching maximum, and you join those points. So, now if you were to design this reactor, first of all, what does it mean that you will reach saturation? First of all, strictly mathematically speaking, as you approach the equilibrium conversion, the rate of reaction goes to 0. So, the rate of increase in conversion will also go to 0. That means, equilibrium conversion mathematically speaking can be obtained only with a reactor which is infinitely long. That is one point, but that besides the point. What is happening as we are traveling along this adiabatic line? Initially, at least the temperature is increasing, so rate of reaction is increasing, but if you cross this particular point, let us say that point was over here. So, if you cross this particular length of reactor. If you have a reactor length which is higher than this, you are actually utilizing it in an inefficient manner, because rate of reaction is lower. So, what should you do instead of that? This is what is precisely done in the reactor design. So, before we go to that, I also want to point out the following factor. See, suppose we start with this temperature T1, then we will travel along this line. Okay. Suppose I start with temperature T2, I will travel along this line. Temperature T3 over here, I will travel along this line. What are the characteristic of these 3 different temperatures and 3 different lines? Temperature T1 is smaller than T2, is smaller than T3. Okay. But in terms of rates, the rate along this T3 adiabatic line starting with T3, you look at again, just keep looking at the color scheme. The rate here is much higher compared to rate along this particular line, that is this, what I am saying is rate, if we start with temperature T3 is much higher than the rate that you would get if you start along temperature T2, if you start along temperature T1, right. But the equilibrium conversion is low if we start with temperature T3. So, that gives us an clue as to how we should run these reactors. Now, what is that clue, or what is that idea? See, in the starting of the reaction, you are not worried about equilibrium, because you are far away from equilibrium. So, you could afford to start a reaction at a higher temperature, because equilibrium is still far away. Okay. So, one way of doing this would be, suppose that we start this reaction at a high temperature, and let me choose that high temperature over here. So, suppose if I start my reaction over here, I think it is not very visible. So, let us use another color. Suppose I start my reaction over here, I am away from equilibrium. So, I can run it, or let me start it over here. So, I can run it along adiabatic reactor. So, if I run it along adiabatic reactor, I will have increasing temperatures, but if I continue along with this path, I am going to hit equilibrium. So, I will stop my reaction, or I will consider I will temporarily halt my reaction. Now, so I will start with, let us say, temperature T4. Okay. I start with my temperature T4, run it for some time and then stop it, and do what? I reduce the temperature. So, let us say that I have run my reaction for certain amount of time, and then I reduce my temperature. If I reduce my temperature without doing anything to the reactants, I will travel along this horizontal line. So, what will I have? I will have same conversion, but lower temperature now, and I will once again start my adiabatic operation. So, once again I will travel along a straight line and I will reach some point. I repeat this operation, so that I go back, stop the reaction, cool it. Let me change the color now, because we are in a different region. So, again I go and I will keep on doing this behavior such that I will have higher and higher conversion. So, what is the idea that we are using? We are now using some way of generating a temperature profile which will follow this dotted line, because if you follow this dotted line strictly, you will get the maximum reaction rate. So, in a batch reactor or in a fixed bed reactor, your temperature should have ideally changed along this white line, because that is where the reaction rate is maximum, but that is difficult to achieve. So, I am going to achieve this by various different ways. One of the way, for example, I can think of this is that I will run my adiabatic reactor. So, what will be my operation look like? I will have, let us say, a reactor R1, okay, corresponding to this, then an heat exchanger to remove the heat, followed by another reactor R2, second segment, again another heat exchanger, cooling, again another reactor, and continue this series. So, in other words, let us go back over here. In other words, I will have this arrangement. What am I doing here? This is my heat exchanger followed by reactor. So, 1, 2, 3, 1, 2, 3, 4 that you see here are the reactors, and Roman 1, 2, 3, 4 are my heat exchangers. So, what am I doing? I am preheating my reactor to a high temperature. Why? Because we just now saw that initially better to start with a higher temperature. So, I am preheating it at higher temperature, sending it to reactor 1. So, this is my reactor 1, then cooling it down in this heater. So, that is my heater, this particular operation or cooler. So, heat exchange unit H1, let us say, and then keep doing this operation in a sequential manner. So, what would I have got now? I would have got, if you look at temperature against the length of the reactor, okay, I started with some high temperature, that temperature went up because of adiabatic operation, then I had cooler. So, temperature came down, again went up, again came down, again went up, came down, and so on. So, an optimal design problem, for example, would be what should be the length of this segment, length of this reactor, and to what level should I bring down my temperature. So, this can be achieved in a simple operation like this, or we can achieve it in a more complicated operation, which actually this is an example from sulfur dioxide oxidation to trioxide to in the manufacturing of sulfuric acid, essentially a reversible exothermic reaction. So, what we have here is bed of reactor. So, this is my reactor with 4 different beds. And these are my heat exchangers. So, what I am doing is actually passing the reactor through the bed, passing the reactor to the bed, taking it to the heat exchanger, again passing it through the bed to another set of heat exchangers. So, what we are able to achieve by doing all this is get the best of both kinetics as well as thermodynamics. Let us recap what we saw so far. So, what we have is a reversible exothermic reaction. My thermodynamics tells me that temperature should be low for high equilibrium conversions. My kinetics tells me, so this is thermo. My kinetics tells me that temperature should be high for better reaction rates. So, this is my kinetics. Obviously, we have to strike a balance, because we want high reaction rates as well as high equilibrium conversions. So, how do we try to strike this balance? We try to strike this balance by saying that ideally in the beginning of the reaction, thermodynamics is far from my mind, because we are far away from equilibrium. So, why bother about thermodynamics? So, if you look at plug flow reactor or fixed bed reactor, for example, as a length, and if I say now, if I will see how my temperature is to be manipulated, at the beginning stages I am far away from equilibrium. So, I should focus on achieving the best kinetics. And how can I do that? By having as high temperature as possible. But as my reaction proceeds, if I keep that high temperature, or if I keep the reactor at high temperature, I know I am going to stumble upon my thermodynamic limit. So, what should I do? I should lower that temperature and keep on lowering this temperature, so that I get best of both the worlds. How? By focusing on better kinetics over here and by focusing on better equilibrium conversion or better thermodynamics over here. Now, in an typical fixed bed reactor, manipulating temperature along the length of the reactor is extremely difficult. So, how can we overcome this problem? So, let me say that this is what I want to achieve. So, how can we overcome this problem? We can overcome this problem by saying, so this is my ideal trajectory. So, how will I be able to overcome this problem? That I will not be able to do all this in a single shot. So, one way of overcoming this problem is I will use series of reactors and heat exchange equipment. And what will I try to do? So, this is my optimal. Okay. So, let us say that this is my desired temperature profile. But how will I try to achieve it? I will try to achieve it by one way is I start my reactor at high temperature, let it increase, and then using heat exchanger I bring it down. Okay. So, my reactor operation would look like R1, followed by heat exchange unit H1. Then once again another reactor, adiabatic reactor. So, R2 followed by H2 and so on. So, this is one possibility, right, and I can keep on doing this as long depending on my design criteria. So, that is one way of doing it. There is another way of doing it also. Not suppose, so this would require that we have small reactors, but many of such reactors along with my heat exchange units in series. Suppose I have only one reactor, a big reactor, and how can I achieve the same strategy? I can achieve it by doing the following. Let us say that I have a big reactor, okay, big reactor. So, what will I do? I will run it as an adiabatic reactor. Okay. So, I will send in my feed over here, some feed over here. Then what will happen if I run it as adiabatic? Let us say the temperature starts increasing, like this over here. Then in order to bring down the temperature, instead of using an heat exchanger, I can actually use the cold feed at a different location. So, my feed locations are no longer just the inlet point and the exit point, but I have inlet point 1, 2, 3, 4 and so on. So, if I introduce a cold feed which mixes with this hot stream, what will happen? The temperature will come down. Of course, in this case the conversion will also change, but that is a small detail. So, temperature will come down. So, let it again run in an exothermic manner and let us add another cold feed. So, these are all my cold feeds. So, I have my temperature going up, another cold feed and so on. So, that is another possibility. There is yet another reactor design. So, this is reactor design 1, reactor design 2, and let us look at yet another possibility, and this is along the following line. Now, if you look at what we want high temperature at the beginning of the reactant and cooler temperatures as the reactants pass through the reactor. Now, if you look at the reaction, again I will repeat, it is an exothermic reaction for which I want high temperature at the beginning of the reactor. High temperature means that I have to supply lot of energy. So, lot of energy has to be supplied to preheat this reactor, but as the reaction is going to take place, it is going to generate energy and I know that I have to cool. If I look at this temperature profile that I want, I know that along the length of the reactor I need cooling, because my reaction is generating lot of heat. So, why not combine these two processes in a beneficial manner? What are these two processes? I need to preheat my reactant to a high temperature, and once the reactants enter the reactor. So, let us say that I have my reactor, and let us say this is my inlet, conventional inlet, but instead of that let us try to look at now in a different manner. Let us say that my reactor is actually reactant is actually surrounded by a shell. Okay. So, this is my reactant. So, what I am going to do, what I am going to do is that if I have to send my reactants in a reactor in this particular manner and my products are coming out like this, I am going to actually send my cooled reactants in this shell, so that the reactants before entering into the reactor goes through this shell. Now, what happens as they go through this shell? What is happening? Eventually, as the reaction proceeds along this line, what will happen? This reactants which are generating energy over here will come in contact with, or rather will come in contact with the cold reactant. So, energy will flow from here to here, thereby cooling the reactant stream and preheating the reactant stream. So, what will happen in the shell? In the shell, temperature will increase from this point to this point, and in the reactor temperature will decrease from the inlet to the exit. A clever way of combining both the requirements, that is of preheating the reactant as well as cooling the reactant as reaction takes place. This is what is called as autothermal reaction, and we will look at the design of such autothermal processes in our next session. Thank you.